Dear colleagues, we are beginning the second joint session of the Kharkiv Chemical Seminar and the Kharkiv Quantum Seminar. Our speaker today is Maksym Kovalenko, a full professor at ETH Zurich. He was born in Gola Pristan, Kherson region, the temporary occupied territory of Ukraine. He completed his bachelor's and master's degrees at Chernivtsi National University in inorganic chemistry and received his PhD degree in nanoscience and nanotechnology from Johannes Kepler University Linz, Austria in 2007, and then joined the University of Chicago as postdoctoral fellow studying the surface chemistry and self-assembly of colloidal nanocrystals. In 2011, Kovalenko joined ETH Zurich and Swiss Federal Laboratories for Material Science and Technology. He was promoted to associate professor in 2017 and a full professor in 2020. Kovalenko's group focuses on chemistry, physics, and application of inorganic solid-state materials and nanomaterials. In particular, present research efforts concern the precision synthesis of highly luminescent semiconductor nanocrystals, nanocrystal surface chemistry, exploration of novel semiconductor materials by solution and solid-state synthesis, and novel semiconductors for hard radiation detection. He has been the recipient of highly prestigious awards including RC Consolidator Grant, Werner Prize, Reusler Prize, Dan Median Prize, and Welland Medal and Lectureship. He has been an acclarative, highly cited researcher since 2018, serves as the associate editor of Chemistry of Materials, and was a chair of the Institute of Inorganic Chemistry in Zurich from 2018 to 2019. Professor Kovalenko was a speaker at the Kharkiv Chemical Seminar in 2022, and today he is a speaker at the joint session with the Kharkiv Quantum Seminar. Dear Maksym, floor is yours.
Thank you, Valentin, and good afternoon, everyone. And it's always huge honor to speak to a seminar organized by the esteemed Ukrainian colleagues. So I will talk today about the quantum light sources produced by chemists. So this is the focus of today. And but of course, I cannot stand to first introduce the big motivation for us for many years. This was the discovery of colloidal quantum dots of conventional semiconductors early in 80s, and then chemical methods for producing highly precisely engineered quantum dots of these in early 90s. And one of the 3 Nobel Prize winners in 23 in chemistry was Munji Bawendi, who introduced these colloidal dots. And just to emphasize what colloidal is that they are produced in a solvent dispersion, and they are often handled in that dispersion. And then you actually put, and to attain that, you have to put a layer of organic molecules around them. So it's always a hybrid organic-inorganic entity. And because of that high temperature method, and these ligands, they could control the mean particle size very precisely with very narrow size dispersion, so that you eventually reach molecular-like absorption features and in many ways behavior. So highly confined quantum dots. And so the HOMO-LUMO gap, or the bulk band gap of these semiconductors, is then scaling with the dimension if you go strongly below a certain dimension of these. Now I was actually myself, this was well before I studied chemistry, and I studied chemistry myself a bit later. So in the meantime, in mid-90s, there were also core shell nanocrystals developed. That's where the inorganic core was extended by the epitaxial shell, so that you keep the same crystal structure, but you keep growing a wider bandgap semiconductor so that you confine the electron and the hole to the core. And so they are no longer sensitive to all the dendrin bonds at the surface, and you drastically increase the radiative rates. So you actually have very bright emission, which is approaching these days 100%. And because of that epitaxial overcoating, you actually see a burst of commercial applications for about 20 years, initially in some bio-labeling, bioimaging arena, and then in television displays. Actually, that's the main application which I believe eventually earns a full recognition to this class of materials and the Nobel Prize to those who invented and developed them. And what you see in comparison to organic molecules, you get much narrower emission bands, you have higher photostability, and you have this wonderful size tuning and tuning of other properties by size and shape. So this is a quick story of conventional quantum dots from the conception to their Nobel Prize and to their commercial applications. Now, as I said, I myself just began my studies as chemist in Chernivtsi. I was born, as Valentin mentioned, in Holopristan near Kherson, which was flooded and then occupied a few years ago. But I grew up mostly in Chernivtsi, in Bukovina region, and studied chemistry in Chernivtsi. I briefly also worked in Kyiv, and then I moved to Austria and United States and then Switzerland. So back then, I was privileged actually to work not on bulk cadmium telluride, but on the colloidal quantum dots of cadmium telluride. So my supervisors back then, Larissa Pavlovna Sherbak, Petro Ivanovich Fejchuk, and Oleg Elpidiforovich Panchuk, they actually asked me to work on this topic, and I was very happy, and still to this day I'm very grateful for that choice of topics that I got from them. And so for many reasons, and initially because of these wonderful colors, you get this very bright emission. But of course, back then we could not afford these sort of organometallic, air-sensitive reagents and things like that. So we worked with much simpler chemistry, and that turned to be equally or comparably good. We had a lot of tellurium. So from tellurium you can produce hydrogen telluride. Hydrogen telluride you bubble through water, and then which contains heated reagents, and with a bit of heating you easily produce cadmium telluride quantum dots. And then I moved to Austria, where we extended such approaches to the infrared spectral region in the group of Wolfgang Heiss. Then I was a postdoc working on surface chemistry in the United States, but that part I skipped. And now we land to Switzerland, where a few years after I began my tenure track professorship, we started to work on a new class of semiconductors, which are known as lead halide perovskites. And these share the same crystal structure as conventional perovskites, but they are different in composition, and now they are semiconductors. And when they are made of lead and halogen as a framework. And then here on A side, which is the largest ion in the lattice, you have a choice generally of these three large cations, cesium and methylammonium or formamidinium. And so this is relatively narrow compositional range, which, but still there is so much work being done worldwide, because with new semiconductors, people started to do all kinds of applications, from X-ray to gamma to photovoltaic. Actually, photovoltaics is the main, but also quantum dots. And this you can produce from solutions or from melt. We grow also bulk crystals and work on them in our team. But I will now talk to probably a bit more recognized invention in our team, which is quantum dots. And before I talk about quantum dots, I would like just to highlight the key difference to normal semiconductors. Normal semiconductors have band gap, which is sort of homo-lumo gap, right? The bonding and anti-bonding style of band gap. Perovskites have actually band gap between, in chemistry terms, between anti-bonding states. These lattices are way more ionic. And for a number of reasons, you then do not have mid-gap states, because your loss of ionicity and this type of bonding, your halide vacancies, for example, leave you states which are resonant in the valence band, whereas your metal vacancy, which is way less likely to form, would be just a shallow state, shallow trap. So these semiconductors immediately were recognized to be way more sort of tolerant to impurities, to structural problems and imperfections, and they were termed sort of defect-tolerant semiconductors, to contrast them from conventional semiconductors, which are super sensitive to any imperfection. And so this is our initial invention by the first of my students, doctoral student Loredana, and Sergey actually was a big driver on spectroscopic characterization back then. This was the first synthesis of these quantum dots of this new type of semiconductors. And as you've just seen in the video, in a few seconds, you get very bright emission without ever needing to overcoat them with epitaxial shell. And that was super motivating for many of us and for the whole community. So yeah, and why this reaction is that fast? Because your precursor is already ionized because of the mixture of these long chain acids and amines. You have ammonium, long chain ammonium, so which stabilizes your bromoplumbate, and therefore you already have a lot of these species to co-precipitate with cesium. Nevertheless, despite this sort of fast ionic co-precipitation, we did get reasonably monodispersed quantum dots. And then we extended their compositions and their to mixed halides or to mixed or to hybrid compositions, formamidinium, then methylammonium, and that became very popular type of quantum dots to sort of replace cadmium-based ones. Now, and a much later advance was that we finally could slow down this formation, so by a lot. So now you see the synthesis, which is just like 2 orders of magnitude slower. So you go like 30 minutes to evolve to get to the same size. So you can precisely control now the size, and you see this very sharp molecular-like transitions at very small sizes, very similar to those classical cadmium chalcogenide-based spectra you've seen from Bavendi before. So by now, there is full control over the size and the formation of these dots. They can be spherical, they can be cubic, or other shapes. And since last year, they also have become a commercial product. The first, as a television display. As dispersions, they are produced by 10 years now. But as a television display, the first examples are in China, and I'm sure some other major brands will follow. And that's quite peculiar, because you now have 2 very different worlds in terms of quantum dot bonding, in terms of in chemical perspective. So, for example, you do have highly covalent bonding in conventional semiconductors. You have highly ionic, much softer lattice. Nevertheless, each of these can be very bright emitters for very classical applications, such as a television display. And so that's usually was the end of the story in most cases about 5 to 10 years ago. So the deployment of them in conventional sense. But then we started to think of what can we do way better, way more academically interesting on a longer term, also maybe very practical. And we will talk about the photon statistics briefly. So from the beginning of the days, we had suns and we had a lamp. Actually, lamp we have only for 150 years. And lamp is a super Poissonian light source, right? The photons come from thermal sources. Everything which is warm and emissive sends bunches of photons, highly bunched photon source. What then people have come up with a laser, which is still classical, and coherent source, which had transformed our civilization by a lot, right? And we have lasers on daily use. And these days, actually, for about 10 to 20 years, there is a huge demand on quantum light sources, where you do control statistics at a sub-Poissonian level. And the most fundamental is to produce just a stable stream of individual photons. And these are considered as ideal sources for information science and technologies, basically, and all kinds of quantum applications, which we will briefly mention today. And so what some of the properties you really want from your single photon source And typically it's a two-level system, like a molecule or a quantum dot, that it emits many photons per second. And so if you have a 1 nanosecond radiative lifetime and you sort of run this gun of photons like at full saturation, you would imagine, and continuously, so it never gets stuck, you would get basically a billion of photons per second. So this would be a very bright source, a very bright quantum dot, and it will compete then in some of the applications pretty well. The hard part is to really produce that stream, and so that those photons, that this is not interrupted, that they are identical and of a suited wavelengths and polarization and everything. This is huge, and this is hard to accomplish. And so this is an excellent problem for chemists and for physicists to work on. So what you see these days in terms of single photon sources are actually very few, and one of them is the epitaxial quantum dot, and it's even been developed by a French scientist and a company called Quandela. And this is probably the only example I would highlight where the light source is actually quite well established, because this is epitaxial 3-5 quantum dot. In these epitaxial layers, there is this dot buried, and that's very stable, very fast, a single photon emitter of identical photons in the near infrared spectral range around 900 nanometers. So it's well compatible with all the detection methods and things like that. And so a lot of other companies, and there are billions and billions invested into this hardware, how you will do the quantum optical computing, how you will handle those photons to produce all kinds of logic operations with them and things like that. But the very heart of this device is a light source. And that light source is actually one dot. And so these are dots initially produced in continuous layers of these, and then you then go and find with microluminescence those dots which are really good, and then you do a lot of microfabrication around that to produce these pillars with very directional emission, and you further tune, let's say, the fine structure and some other emission parameters through some electrical fields which you can supply in that complex heterostructure. Huge progress, huge invention, huge achievement, I would say. Question for us is, can chemists do something comparable, maybe different, maybe with its own advantages, or maybe inherently more advantages? And this is something what I think is to be answered, and there are very good results on that path, which I will share with you today also. And if you are interested to read more, this is a paper by another group, but this paper covers most of other single photon sources and what are the requirements and what is the state of the art there towards the use of photonic qubits basically for competitive computation. Now, when you want to look at a single dot, what you do, and that's very important to discuss, you need to put these dots apart from each other. And so you need to actually disperse them on a substrate, like a glass substrate, preferably in a thin matrix, like a polymer film. So the distance is microns between these dots, and that they are one by one, in a random manner at least. And then you go confocally and you excite them and collect the emission, and then you can read the spectra of these, so from one single quantum dot. Or you can also do photon statistics. So you send your stream of photons on a 50-50 beam splitter, which means that if these photons arrive one by one, they may arrive either on one photodetector or the other. These are very fast APDs. So they can, and then you look at the correlation of the signal between them under CW or pulsed conditions. So in simple terms, at the time equals zero, zero, which means zero delay between these two signals, you will see only one or the other one with the signal, right? So that's this autocorrelation, second order correlation function between these two must be ideally close to zero. Or in other words, if you throw there is a one ball on it during the football match, you can never score a goal simultaneously in both gates, right? So it can go on one or the other, right? Same here, if there is only one stream of one photon at a time. And of course, you may do it at room temperature or at low temperature, and there are good reasons to do both, because there are applications which require quantum dots at both temperatures. And this is how, with a wide field camera, for example, such a single quantum dot looks like at room temperature. So this one is relatively good, it's stable. There are some less stable ones which blink, so they go on and off, and this is what you don't want. Initially, we were looking at these dots. Now we look back confocally at single dot, but we now cool them down to cryogenic temperatures. And then they were extremely stable because there is only vacuum, and there is high vacuum, cold environment is ideal to preserve the stability of these entities. And that's the work we began about 10 years, actually more than 10 years ago, with excellent collaborations at IBM in Rüschlikons, which is across the lake, a fantastic research lab. And they looked at these dots and they saw that they were quite stable, so minimal blinking. Quite good single photon sources, because it has to be below 0.5 to qualify to be generally a single photon source, so to be sub-Poissonian in terms of statistics. And they were tunable, and they were easy to make. So this is fantastic news, which motivated us to continue. And then we continued. And before I show next portion of results from that time, let me explain you what do you want to see from a single dot. When you look at a single dot and at a low temperature, you actually get rid of ensemble averaging. So because otherwise your spectrum is way broader because of many dots. And you also get rid of homogeneous broadening, which is coupling to lattice vibrations or molecular vibrations for single molecules, which also make your lines broader. And you may also see or not the extern fine structure, so some intrinsic substructure to the emissive states. And you may then see an inherent radiative rate. So how fast is that emitter, which, as you remember, we care a lot about. And that's what back then Gabriele, who was back at IBM, and now he is the senior scientist in our team at ETH Zurich. That's a wonderful discovery back then. We could see that these dots are very fast emitters. Actually, this is 0.2 nanoseconds. So way more than, even more than a billion photons per second, theoretically, you could expect from such a single photon emitter at the saturation. Now, this was puzzling to us, because normally, if you cool the dots to low temperatures, semiconductor quantum dots, they emit through the singlet state, because this is total angular momentum, and that's a good selection rule for the emission, for these optical transitions. Total angular momentum of an exciton of this entity, electron-hole pair. And when it's singlet, in this case, it has to be slow, because it's sort of forbidden. And when it's triplet, it has to be bright and fast. And normally, triplet is above singlet, and therefore, most of quantum dots are slow emitters. But these ones are fast emitters. And so we could sort of immediately understood that that they must be emitting through the triplet state. And so, may I ask, Andrei, your hand, you raised your hand.
Yeah. If I may, just since we are on this slide, could you shortly comment the negative time? What does it mean here physically?
Well, it's not really negative. It's just sort of response of this device, sort of. Yeah, it's not really negative. Yeah.
Oh, okay. Thank you.
Yeah. Now, another big discovery was that this is T1. So how fast is your recombination? And then there is T2, which is very important to consider, which is how long these emissive states preserves the coherence. So, because basically what you measure as a photon property, coherence, retention of coherence is transcribed from your light source. It's actually perfectness of your light source. And of course, you want that your decoherence times are equal to basically 2 times T1. And that is so-called Fourier transform limit. And in that case, you do expect that these photons are fully indistinguishable. And then you can do some sort of operations like quantum interference. And of course, there are no many emitters which do that because everything is against your material. For example, the lattice vibrations are cause for decoherence, maybe electronic noise, and everything is against you in maintenance of coherence. But if you do get it, you could do this so-called two-photon coalescence, or in other words, quantum interference, and that's very fundamental proof that your photons are indistinguishable, and that these light sources are suitable for optical quantum computing eventually, or other applications which require optical coherence of these single photon sources. And here, this is actually a figure from the paper by Munji-Bawendi, who studied many of the single dots with these in these two-photon coalescence experiment, and they could see, and obviously, if that is the case, that there is coalescence, then they must exit on one or the other beam splitter and not in a statistical manner. So basically, you compute the theoretical pattern, the gray one, which is fully statistical, and the one with two-photon coalescence, and the amount of this deep is a measure of how much of that indistinguishability you do observe. And for very good photon sources, single photon sources from like those specific case of epitaxial dots, this goes to well above 90%. And now with colloidal quantum dots, for the first time, we could see that happening in the lab of Munji-Bawendi. 3 dots were reported, and this is just one of them. And generally, as a chemist, you ask, and this is a TM image of a sample, and of course, as a chemist, you ask yourself a question: what does govern these T1 and T2 numbers, right? And or which of these dots, what size, what shape, are better suited for this type of, because you cannot really know that unless you are able to go and find that dot, which is nearly impossible. And so that leads you to look closer at these T1 and T2. T2 is really a mystery for now, and we don't know much about that, so we will so far discuss only T1. And so the way to approach that equality, this Fourier transform limit, is to make T2 as long as possible and T1 as short as possible. And so when you look at the golden Fermi rule, you know that your rate of your transition, so the T1, will scale with the intrinsic property, which is the oscillator strength in your transition, and local density of states, which you can engineer by external cavities and things like that. That's what people do with epitaxial dots these days. We are not there yet to engineer those extrinsic factors. But what we will look at is the intrinsic oscillator strength of these emitters. And that's basically, typically, you would imagine that this should be sort of constant. It's a property of that specific material. But what if not? And that brings us to Emanuel Rashba, who is, as some of you might know, is the one who came up with the concept of giant oscillator strengths at the end of the 50s, early 60s, who was a lead theoretical scientist in physics of semiconductors in Kyiv, actually. He studied physics at the Kyiv University, and then was for many years a scientist at the Institute of, I believe, Semiconductor Physics. So famous scientist who came up with a lot of textbook semiconductor physics, including physics of weakly confined excitons with some localization. And so some of these ideas are actually very well translated now to quantum dots which we are talking today about. So this is a beautiful result of the very meticulous work of our student Chen-Lan Zhu, who measured many single dots, and she could demonstrate that eventually the larger they are, up to a certain size, the faster they emit. And that's quite incredible because, okay, at smaller sizes, you are roughly the size of the exciton whole pair. So you are in a strong quantum regime, or actually a bit smaller than that, which is roughly, depending on material, but we talk about 5 to 10 nanometers, depending on halide used in the perovskite lattice. And now, as you increase the quantum dot size, let's say from 5 to 30 or above, you actually increase the volume by orders of magnitude, and the quantum dot just becomes a faster emitter. So there is no intrinsic reason for that to happen, and it's radiative. There is no intrinsic reason for that to happen than increasing these intrinsic oscillator strengths, which is generally you would term it a giant oscillator strength effect. And that at a single particle level. Of course, we are not first to observe that. When after Rajba, for example, when he proposed that effect, then it was seen in some molecular systems. But in terms of semiconductor quantum dots, the very first observation were by the groups in Japan. Copper chloride quantum dots emissive in the ultraviolet spectral range with very small excitons, actually. You do get acceleration of the emission up to the very large, sort of large ratios between the physical dimension of a quantum dot and the exciton Bohr radius or diameter. So this is again at low temperatures, and this is a manifestation of that giant oscillator strength. But this is at the scale of ensemble. So this is a glass with copper chloride, doped with copper chloride, basically. In our case, we see that at a single particle level, so that we can combine the effect of giant oscillator strengths to accelerate the emission, and still a quantum dot behavior seen as single photon emission. So long story short, making dots larger up to a certain size, which is roughly 5 to 8 times the natural dimension of the exciton, 1 mod exciton in these materials, you do accelerate emission by a lot, and you still maintain single photon luminescence from these fluorescence from these dots. So these are very good news. These are some of the fastest emitters, spontaneous emitters, which are known. And of course, you would expect that rates of emission should then, rate of absorption will scale with the rate of emission. And the way to see that, you can even see that in a linear absorption spectrum from the film of these quantum dots, which is a polymer, let's say, film containing an ensemble of dots. And what you see on this figure, for instance, that is a gray spectrum is a conventional room temperature, a linear absorption spectrum. So the features are very blurred, right? Because you have very strong exciton phonon coupling at room temperature and some size dispersion. But then as you cool it down to cryogenic temperature, so you freeze out the coupling to vibrations, you see much sharper excitonic lines. And if you go with that language of S, P, and D type excitons, you see that somehow one exciton becomes way sharper and more intense than 1p exciton, which would go quite against the degeneracy of these states. And then our wonderful collaborators looked at this long-range electron-hole correlation which builds these giant oscillator strengths, and they could see that long-range correlation, it actually enhances this excitonic transition oscillator strength, but way more for 1s than for 1p, and therefore you get then way stronger 1s to 1p ratio. And that ratio actually scales then with how much radiative rate is enhanced as well for the same size quantum dot. So basically, we now combine these two stories, right? This much faster emission and from single dots and much enhanced 1s to 1p absorption from these ensembles. Of course, the future experiment which we still would like to see is absorption experiment on a single particle level, which should be possible eventually with some tricks. Now, getting back to some challenges. So with these emitters, we now need to look at the crystal structure and the surfaces, and these are the challenges to handle, especially as chemists. So the crystal structure for this one, cesium lead halide, which is the most prominently studied material system in this case, these ones are orthorhombic intrinsically. And so the emissive dipoles are also non-degenerate. So this bright triplet has three components because of these intrinsic orthorhombic lattice. Another thing for chemists, because actually I believe we are here chemists / physicists / interdisciplinary crowd. And so I try to reach to both of you. I'm a chemist myself. So for chemists, the bonding here is non-covalent, right? You have a long chain. One of the types of molecules you can put on the surface is that you have a positively charged a long chain sort of ammonium salt, and that replaces locally at the surface cesium ion, and that's the way you can attach a long chain molecule so that you can keep a colloidal state. So this, because of this hydrophobic nature of these lipophilic nature of these chains, you basically can disperse them in apolar solvents. That's why we initially emphasized that quantum dots are always, or nearly always, chemically made dots are organic inorganic entities. And so now the result of that, as we discussed, orthorhombic asymmetry, is that the triplet state is non-degenerate. It has three components, three orthogonal emissive dipoles, and that you easily see in the high-resolution emission spectrum at low temperatures. And you see this polarization data as well for these three dipoles. Now, obviously, no matter how stable that emitter is, the combined emission of these is basically they fire randomly these photons in intensity, in a number ratio, which scales basically as shown here. So this is not a source of truly indistinguishable photons, right? They are distinguishable. So ideally, you want to have these degenerate, and that's what in epitaxial world they do by applying electric fields and other tricks. We are not there yet, but one way to handle that problem is through shape anisotropy. And in the most recent results, we could see that if we keep the same volume of a dot, so to keep the same giant oscillator strength of your transition, and so that this is still a fast emitter, but just elongating these nanocrystals in one direction, so making these cuboidal nanorods, so they have a square cross-section and they are elongated in one dimension, you can actually get rid of these three lines and you get only one line. And that's because you alter this fine structure splitting, and the lowest of these will be the one elongated along the nanorod. So you keep single photon emission, and you further accelerate the emission because of reduced electron-hole Coulombic interaction because of this shape. So that's how we conclude here on the radiative rates at low temperatures. You simply see here the fastest quantum dot emitter that we know so far, in the absence of any cavity to alter the radiative rates by the local density of states further. But that's already fast enough for many applications. The future, of course, here is to further engineer the emission color. So far, we mostly discussed the green spectral range. That's where the material was ready, way more ready for the spectroscopy than our red emissive dots. But eventually, you may go to tin-based perovskites and further into infrared, depending on technologies you target. And this I will only briefly cover because there are a few other topics I still would like to cover. and to save the time, this is just to show you that not only this linear polarized single photon emission is possible, but here you see the first demonstration of a conversion from achiral, so linear polarized, to fully chiral emission, and at the same time single photon emission, just by physical proximity of the perovskite quantum dot to a highly chiral plasmonic structure, plasmonic, these cuboidal, helicoidal, they're called helicoids because of the chirality here. They are produced by the group of Kita and Nam at Seoul National University using chiral thiol ligands during the selective etching of these of the non-chiral cubes, and then you statistically can spread your quantum dots over these much larger cubes, and then you can find in your microphotoluminescence that some of them acquire very high degree of chirality. So you see very high dissymmetry factors and the degree of chiral polarization up to, in some of the best cases, 60–80%. And good correspondence between handedness of the excitation and handedness of the emission. I apologize for rushing through that because of the other topics to cover. So this was about single photon emission. Can be fast, can be at a low temperature fast, and linear polarized chiral. Obviously, there are many applications of that. We mentioned quantum computing. There are quantum communications, which is probably on a near term way more feasible. Quantum communication, quantum imaging, and quantum sensing also. But of course, you dream on a longer term that you can control these quantum emission through the discrete bundles of photons, right? There are some reasons to hope for that. One of them is the observation of superfluorescence, which was the first ever observation of that phenomenon in conventional solid-state materials. Again, through the wonderful collaboration with our IBM colleagues. They were looking at the superstructures of our quantum dots back then, and they could see much accelerated, again at low temperatures, accelerated emission with this ringing, with the excitation fluency dependent emission rates and build-up times. So here it's physical, this build-up time, and with some bunching in these emission bursts, and then as chemists we continued to engineer that property by the structure. But in a nutshell, what you see here, that in a sub-wavelength volume in this superstructure, the number of dots, and we estimated between 10 to 20. The emissive dipoles basically couple, synchronize, and emit as one giant dipole. That leads to fast radiation rate. And through oscillation, because of this coherent reabsorption during that process between the light field and this giant dipole. And we kept playing with how that property evolves as a function of the structure, where you could introduce a dielectric separating dots between these emissive dots. And then our IBM colleagues discovered how to introduce the superstructures into some of these cavities for potential on-chip integration. We could also study these in relation to exciton diffusion by making all perovskite superstructures. So this is a very interesting area to engineer collective response, which comes from what we discussed initially, from long coherence of these excitons at the single particle level, such that they, in a certain regular structure, they have enough time to build larger collective properties, such as coherent emissive dipole across a number of dots. And coming back to chemistry, so that our chemists can also enjoy some of the chemistry aspects of these, I would like to highlight the engineering of the surface chemistry here. what we briefly discussed is the use of long-chain ammonium salts. As an anionic ligands, you could also imagine if you displace your surface halide with your anionic group, but that's way less effective than cationic binding. But what turned to be way more robust is to have a zwitterionic ligand, which features negative and positive group, and of these, they bind with two groups to the surface, and of these, phosphocholine and eventually synthetic phosphoethanolamines turned to be the best. And that's where the study began already almost 10 years ago with synthetic, with actually commercial. Some of these are natural, such as lecithin, zwitterions, which for the first time could render our dots stable across very large concentration range. And then through these chemistries, you remember this slide where we developed a new synthesis. So now we can apply all these new ligands to nanocrystal surfaces through the ligand exchange and see how much that improves our single dot behavior, right? But also besides single dot behavior, this helped us to demonstrate a few other types of hybrid perovskite quantum dots. One of these I would especially highlight because I think I've seen in the list of attendees Ilya Guralsky, whose group actually was the first one to demonstrate bulk perovskites with this new cation, which is elusive cation. Normally, organic chemists would not like to have it because it's super unstable, unlike to the molecule which is what it is made of, which is aziridine. But once you incorporate into this A site lattice, on A site in the lattice, you actually stabilize the perovskite. So it's an excellent synergy. And the way we produce quantum dots out of this idea of Ilya is that we took aziridine, so the stable one, and our molecular approach to producing quantum dots. And then in an aqueous medium, we could produce very monodisperse colloids of this impossible salt. So that's a beautiful, that's quite peculiar in its own. And then another example is monomethyl hydrazinium, which is even slightly larger cation, but still fits to the A site. And that's the work we produced. These they were known as a bulk material, but we had to find a way to produce uniform quantum dots of these. And that material has peculiar structure because in the crystal structure you have layers which alternate each other. So non-distorted layer and the distorted layer alternate each other. So from structural viewpoint, you have a perovskite which is three-dimensional. So all the octahedra are connected in 3 dimensions, and that actually allows you to produce quantum dots. But from the perspective of electronic structure, you have sort of 2-dimensional sort of localization of your you expect at least 2-dimensional localization of one of your carriers. And that actually you do see also in the emissive property. We see 3 types of emission lines also at a single particle, not only at the ensemble, but also at a single particle level, which actually emphasizes the value of single particle spectroscopy, because that way you can prove that these extonic features is not just a population of 3 very distinct types of nanocrystals, but that exists in one lattice. And you get in one lattice, you get self-trapped extons, which are slowest in the emission. Then you get some intermediate sort of dimensionality excitons where the hole is localized and the electron is delocalized. And these are a bit faster and a bit higher energy. And then there is intra-layer 2-dimensional so-called free exciton, which is faster than the other 2. So, but overall, at this stage, with these materials, you do not get any further improvement in terms of emission properties. So this will remain as an academic example of what is possible. Now, coming back to our phosphocholine and phosphoethanolamine ligands, this little shift from natural product lecithin to synthetic phosphoethanolamines which is just a change of this quaternary moiety to primary ammonium moiety, was a huge improvement in our experience as chemists and as spectroscopists. So this is great work. Especially, I would emphasize Andrei Baumgartner's theoretical chemist from Lviv, from Condensed Matter Physics Institute, I believe, of the National Academy of Sciences, who is our long-term collaborator and who trained Andrei to do some of these molecular dynamic simulations. So they showed that in silico, and then our experimentalists showed that also in the flask you do get way improved binding of these ligands, and so you can adjust also the distance between ammonium and phosphate moiety, and you can adjust these chains to make these nanocrystals compatible with all kinds of solvents. And yeah, so this was a major synthetic work and theoretical work, but that paid off a lot. So first of all, it's extendable to all kinds of soft metal halide nanocrystals, not only emissive perovskites, which we discussed. It's also making your quantum dots compatible with industry-friendly solvents. So this is the one way preferred by the electronic industry to produce optoelectronic devices. And you can even do catalysis now, since you can engineer the ligand coverage, so you can engineer the access to the surface. And this is a beautiful collaboration with the group of Eric Carrera, where they have chosen and demonstrated selective bromination of certain substrates with very small quantities of these quantum dots as photocatalysts. Some of these reactions they have proven to not be accessible through blue light catalyzed photoredox catalysis by conventional transition metal based or organic photocatalysts. So, coming back to single photon emission, in the very last few minutes, we will talk about room temperature emission, because for many applications, you do not really want to have your emitter at low temperature. You prefer it to be operatable at room temperature, and you may lose extonic coherence because this is intrinsic. The exciton phonon coupling is unavoidable, but you gain a lot in practicality for some applications. And here I would like to emphasize that when we prepare these samples for single dot spectroscopy, you remember initially we discussed you need to disperse them microns apart of each other. So you have to actually dilute your colloid by tens to 100,000 times. You get very homeopathic sort of concentrations, and by doing so, you basically multiply the ratio between the residual moisture and residual oxygen, which is unavoidable in a solvent, no matter how dry is that. So you multiply these residual enemies with respect to your quantum dot, and plus the ligand desorption, even these best ligands, will cause damage to the surface and potentially the loss of the ligand. And that's what I try to emphasize, that by shifting from just a quaternary to primary ammonium salt and much stronger binding, this already could translate into huge improvement in the survival rate of these dots after such massive manipulations, dispersions and everything. So you see statistically that these are the spectra from single dots over time, and you see that they are retained way better than the best ligand before. So now, and that's at room temperature for hybrid perovskites, which we could not even study before. That's huge happiness for us back then, because now you can see these for hours. They stay bright, they stay almost fully in the on state. So you see here on to off ratio, they are mostly, they do not blink like stars on the sky anymore. And they are wonderful, stable room temperature, single photon sources. And that's what the student Leon Feld just published and graduated in our group. He was looking now with these new improved colloids, he was looking at the single photon purity. You remember the lower is this G2, the cleaner is a single photon stream as a function of size. And he could see that with hybrid perovskite quantum dots, you get very good retention of single photon purity up to large nanocrystals and even larger. And that is, again, for the first time, the gift of nature in these materials. The reason why it's unusual is because normally the larger the quantum dot, the more likely you get contributions from biexciton at room temperature. And you cannot separate them because it's all mixed in one emission band. And because a larger dot can afford basically a longer living biexcitons. And the usual way to keep biexcitonic emission, so this is biexciton generating two photons, the usual way to get rid of biexciton is just to keep the dots very small. But then they are very unstable, and that's a trade-off you can never solve. Now, with our quantum dots, we can break these of hybrid composition, formamidinium, not cesium. We break this sort of volumetric dependency, and Leon came up with a beautiful hypothesis that now not the physical dimension which matters for the Auger-Meitner recombination of biexciton, but it's actually local wave function localization which at elevated temperatures like room temperature originates actually from that lattice sort of dynamics. So these materials are inherently highly entropic. There is a lot of motion. Moreover, I briefly show this paper also. Moreover, this is reflected in the entropic contribution to their free energy formation. So the entropy here is actually way higher than for any more rigid semiconductor. And that actually probably the reason these lattices even exist. And so what he did, he simulated this wave function localization of holes in this case, and he could show that your basically exciton is not permanently localized anywhere, it moves around. So it is normal Wannier mode exciton, but it's dynamically localized. And that is a hypothesis why the Auger-Meitner recombination is greater in these materials, and you can drive these emitters at room temperature to basically saturation while maintaining good single photon purity at low excitation fluencies and also at high excitation fluencies. And that is true also across all hybrid perovskite quantum dots. So this is consistent with this idea that once they are hybrid, they are way more structurally dynamic, and they inherently will be sort of purifying, getting rid of biexcitons at room temperature, giving you stable single photon sources at room temperature. So this was basically the end. And as a summary slide, I want to again remind those who might have come a bit later, I wanted to remind that unlike to classical light, which comes in either super bunched or super Poissonian or Poissonian, which is conventional thermal sources or laser, we now work on quantum dots, which are sources of quantum light. And we began about 10 years ago showing relatively pure but still unstable single photon emitters. These days, then we could see much improvement in single photon purity, still with limited stability. Then record fast emission. And these days, we also start to observe fast and stable and hopefully eventually intensity squeezed and indistinguishable photons for all those quantum applications, which we briefly mentioned before. With that, I would like to highlight this wonderful team of chemists and physicists which I represent. I am the spokesperson for these. The group is quite a bit smaller now. This is a photograph from about a year and a few years back. But still, there is a huge diversity in terms of competencies and activities. And thanks to all of you, and I will be happy to take your questions.
Thank you, Maksym, for a wonderful presentation with fantastic results. We already have raised hands. First one is Metro Anohin, please.
Yeah. Do you hear me?
Yes, Metro, yes.
Mm-hmm. Thank you, Maksym, for this very interesting presentation. I have one question. It may seem stupid, but nevertheless, your central topic of your study, as far as I understand, is call it perovskite. And yeah, my question is as follows: why did you choose lead as the central element of perovskite structure? And how does the choice of the central element affect on the properties of quantum dots? Because yeah, it is also not so environmentally friendly element.
Dmitro, first of all,
Why not?
great to see you again. And yeah, lead, there is not so much choice because, well, lead is supposedly good for a number of reasons. It has good spin-orbit coupling, and that somehow improves the band dispersion in conduction and valence band. So it's good for semiconductor, actually, good strong spin-orbit coupling. And then another one you would expect to do similar would be bismuth, but bismuth is three-valent. And so when you try to make halides of those, you don't get the same structure. You don't get corner shared structure. You get face or edge shared, non-perovskite lattice. So different crystal structure gives you different band structure. And so we are just quite restricted to lead. So the only faithful alternatives to lead are tin, which is very good choice. So Dmitro, I would say tin has future. The only problem with tin is instability. Tin and germanium, but germanium is way worse. Tin is a good alternative, but tin 2 plus is very unstable against tin 0 and tin 4 plus. And that would be okay, but on top of that, tin-based perovskite have very low formation energy for tin vacancies, and that leads to self-doping of p-type. So this compromises a lot in terms of intrinsic semiconductor property. We do work on that, so we will soon publish one paper where we show how to improve that, how to fight against that self-doping while preserving these materials from oxidation. And we will show in future how to do compensation doping, which we're working on. So long story short, Dmitro, there is alternative and only one, which is tin. All other halides have problems or end up with highly self-localized extons, which are way slower as emitters.
Okay, yeah, I'll think about tin, but we have a challenge of stability. So that's more or less clear. Thank you. I wish you success.
Thank you, Dmitro. You too, by the way.
We have the next question from chat. Let me read. I think Daniel Gao asked question. So he thanks you for the excellent talk. And while you showed strong evidence for an excitonic origin of photoluminescence, much of the literature still treats the emission as band-to-band or combination. In your view, is this discrepancy mainly due to differences in experimental conditions and material quality, or is it a more fundamental ambiguity? And do you think this is lack consensus is slowing down progress in the field?
Thank you, Daniel. So at room temperature and below, these materials do behave as excitonic. You have exciton binding energies up to 30 millieV. They're a bit size dependent. You clearly can see exciton binding energies by exciton and things like that. So as you make them bulk, you will get some excitonic dissociated, and then exciton dissociated, then you have more like this usual band-to-band recombination. So yeah. So that's basically there is no problem with that. These are quite excitonic materials in that sense. Yeah, that is an answer, I would say.
Thank you. The next one is Roman Viter. Please, Roman?
Thank you for a nice presentation, Maksym. I wonder about stability of your materials against oxidation and humidity. Just like from practical point of view.
Yeah, that's a very good question. It's always a question for any quantum dot material. You have high surface to volume ratio, you have a small entity. We are a bit protected by this so-called defect tolerance, meaning that just like lack of some ligands at the surface does not kill the emission as it does for cadmium selenide. So cad selenide is very poor emitter without epitaxial shell. Here we don't need that. But still, moisture is specifically for perovskite, highly polar solvent or moisture is a no-go. So we cannot still disperse them properly in water. If we don't need necessarily, but for some applications that would be a need. And a long-term exposure to moisture may compromise their emission as well. So that we mitigate by embedding them into polymers and or between or encapsulation techniques. So long story short, moisture is the main issue for the long-term stability. There is another very specific problem with perovskites because lead 2+ is actually quite electronegative cation. So in some of the devices like light-emitting diodes, when you pass electrons through these, they are much easier to reduce than cadmium 2+, for example, or some other quantum dot material. So it's a bit unexpected problem. Or in the photoredox applications, when you use it as a photocatalyst, you can actually self-reduce also quantum dot with electrons. So you need to do the more balanced charge injection in case of LEDs, or have some sort of hole and electron balance when you do photoredox. Yeah.
So your answer, thank you for your answer. Your answer provoked one more question about quantum sensors. So you showed that, as I understand, you can, that by using your materials, you can detect light polarization. But what about other parameters? For example, magnetic field or some chemical gas sensors. Do you have any opinion and any vision about that? Thank you.
We do have vision. We don't work much on that, but indeed, if you, let's say, have local electric field, you expect some sort of Stark effect, for example, on your exton. Or you were saying with magnetic fields and things like that. But indeed, they may be used as quantum dots, as local probes for temperature, perovskite and or electric fields or other fluctuations. They have very strong temperature dependence, for example, and anomalous for comparing to other semiconductors. So you could imagine sensing temperature as well. But the first step towards all these applications is to make sure you get a quantum dot which is stable for like days and many months, so that what you observe is not just a compound effect of own degradation plus local effects, right? Yeah, but it's a good it's a promising direction. I agree. Yeah.
Thank you.
The next question from Lorenzo Trombini, please.
Hello, thank you, Maksym, for the lecture. Very interesting and very nice presentation. I have just a very small curiosity regarding more the synthesis than the application of these quantum dots, because you showed a colloidal, so it's solution based. So is there any improvement or chance going towards solution-free synthesis? So let's say vacuum based or thermal evaporation. Can this be possible, or can it be translated?
Very good question. And there are even some works in that, because, and also, so vacuum-based or thermal evaporation. So we generally claim that solution production, because you require only basic glassware and things like that, is actually alternative to those. You do not need vacuum. You do not evaporate things. So but still, we do produce some, and we start to publish very luminescent, very bright perovskite layers, which are nanocrystalline. They're not continuous layers, but they are like islands. And depending on the substrate, we actually do in our group thin film evaporation of the perovskites into such islands, and they are also very bright emitters. So that's, and there are other groups report continuous layers or such sort of quasi-epitaxial quantum dots by just thermal evaporation, or by more like a chemical vapor deposition, when you have lead bromide and anticium bromide source, and then they find each other on a substrate. And that's sometimes it's very practical as well, I believe. Yeah.
Okay, thank you very much, and wish you all the best.
Thank you, Lorenzo. I see Andrei Dmitruk. I would love to hear his question.
Yeah. Maksym, nice to see you, and thank you for a very interesting presentation with very new results, as I see.
Thank you, Andrei.
My question about chiral plasmonic structures. Do you produce that metal chiral blocks, or is that from other group, and how you can do that?
So this is invention of Kitai Nam. This is from his group. And I met him at a conference a few years back in Paris, and then we just decided to combine the efforts. So he sends us these helicoids, and they are produced, to my knowledge, from a non-chiral large gold nanocubes by selective sort of etching in the presence of chiral thiolate ligands. And so, and then they have a number of papers how to control that sort of etching. And that etching is not removing material continuously, but it sort of establishes some grooves. And those grooves basically are chiral because the ligand is chiral. And they have shown that this is the origin of chirality. Yeah.
Okay, thank you.
Thank you, Andrei.
Please, Konstantin Lukin, the next one.
Hello, Konstantin Lukin. Want to ask a question?
Please.
In the slide 23 of your excellent presentation, very informative. Fantastic. Thank you for this presentation. But now there is a question. In the slide 23, you showed us the results of the measurements.
Oh, not 23, probably. This one, 24, yeah?
I don't know. Oh, sorry, 21. Sorry, 21.
21.
Yeah.
Yeah.
This one.
Yeah.
You made the measurements related to coherency, the notion, and
so
then...
I didn't comment on these measurements, right? Yeah, please ask your question. Mm-hmm.
Maybe ask question. Maybe this makes your answer easier. The optical coherence time, this T capital 2, and radiative lifetime is equal doubled of T1. And the conclusion that if the photons which you are measuring or registering, detecting, indistinguishable photons, then it means this equivalent to quantum interference.
Yeah. And
this state, if we consider a single quantum system, this state, if it is indistinguishable, is interpreted like entangled photons. Can you give some comments? Is it right impression or is wrong impression on this result?
Do they become entangled through quantum interference? I'm not sure. It's just that their individual wave functions collapse and they become as one in a way. But beyond that, I wouldn't know. Yeah.
Sorry. I kept in mind that indistinguishable photons. If these photons is single quantum state and indistinguishable or non-separable otherwise, then it's interpreted like entangled. And
they're not entangled initially because this is from a consecutive it's a stream of photons, and you just you basically delay some one with respect to the other, and then they arrive at the same time on a beam splitter. So they are generated as.
Yeah, as I understood, you did not make this more subtle measurements.
No, and this is anyway not our measurement. This is Munji-Bawendi's measurement. But yeah.
Okay. No, by the way, this question is related very much to today. We mentioned the quantum sensors and in particular quantum radar design. There's a huge amount of papers published. The key point from the engineering, quantum engineering, is we one of the questions: is it possible to make a computer modeling of this process? This is a very challenging question. That say how you can model quantum mechanics is then to model you have to understand. But as Feynman said, nobody understood quantum mechanics. Just take it like it is and use it. So my question is, what is your opinion? Is it possible to make some quantum, computer modeling of this phenomena which you're dealing with?
I don't know. Honestly, I don't know.
Thank you very much.
We are not there yet, so I will not improvise with something that I'm not that I don't know. Yeah.
No, my opinion is if the whole quantum mechanics is abstraction, kind of abstraction, we could not see directly what is quantum mechanics, but only developing the theory, the notions, the concepts, and so on. I call this abstraction, the abstract picture. Then from general point of view, it follows that we can make simulation. But in many textbooks it's written, forget about this, you cannot. Only later, enjoy later. Okay, this type of questions, there are many these type of questions, but I once again wanted to thank, I didn't expect this so many results in the physics and chemistry, photonics, even the laser. Then the congratulations to you and your team, your colleagues. Thank you very much. And also I would like to thank Andrei Sotnikov as organizer for this excellent. Did you count so many participants? More than 100 participants. Congratulations.
130.
Thank you very much. Sorry?
130 participants we had.
Yeah, 13 is just a reminder, just more than 100. This is the criterion. Thank you.
Thank you, Konstantin.
I
see Olga.
Yeah, please, Olga.
Good afternoon, ladies and gentlemen. Thank you, Maksym, for excellent presentation, like usual. Thank you for support for Ukrainian science. And today I'm representative our team with chemical engineering department from Khmelnytsky National University. And my question was very simply and very easy because it's today we looking for excellent presentation, but a lot of my students joins for this lecture. And tell please about way and how, because it's imagine presentation, it's hundreds hours in lab, a lot of people, a lot of brains, about how time spent for this research and about future of this research. Thank you.
a very broad question. So I first need to understand the core of the question. So you say the future of this research, and then how much time we spend on this research, and how we organize this research, right?
Yeah.
Okay, let's do like that. So future, I think, is very bright because for the first time we have chemically made quantum dots which do have these coherent properties, which are fast emitters, which we know how to handle now. So there is some future in that sense, which is very inspiring. We have collective phenomena for the first time. So it's very motivating. So future, I think we will develop a lot in that sense. Now, how much time we spend and how we organized. We are a big group, and it's a very mixed group. It's chemists, spectroscopy people, some computational work done in the group, a lot of very basic research, advanced solid state NMR, nuclear magnetic resonance, a lot of synthesis work done, organic synthesis actually, and it's a complex team. So you need a number of people. You need a critical mass of people. We actually, for some of these future directions, we actually need a lot more resources and people than we even so far engaged. And that's even a challenge, because when it comes to such interdisciplinary work, you need a critical mass of expertise across all these areas. And that leads you to prioritize. So you do need to rethink. For example, at some point we stopped working on all kinds of other quantum dots just because we worked on them. And we work only on perovskites now. And then, yeah, and so we need to be selective in what we do. And then about my time, I think you may be able or not to cope with any size of the group, depending on how the team and the people, who are the people. For example, I am very blessed to have very good team leaders, very good doctoral students, and then having 10 more excellent doctoral students or more senior people will not make you suffer, will make your life even easier, because the only thing you should not be on their way, so that you don't interfere with their creativity and just keep up with them and keep this resonance. And so, yeah, so with very good team, it's easy to work with a large team as well. So, yeah. So just to give numbers, we are about 20 plus PhD students and about 10 more senior researchers. That's not the largest team, but it's pretty large for me.
Thank you very much, and I hope we maybe some from my master or PhD students joined to your group, or maybe you will be when you will be in Ukraine. Welcome to our department. We will happy see you. Thank you very much.
Thank you, Olga. Thank you. I hope all of this comes true. Thank you.
Please, Ilya Goralski.
Thank you. Okay.
Hi, Ilya.
Thank you. Yeah, hi. Hi, Maksym. Thank you for this presentation. Really nice and interesting. We're listening, the whole group, to a presentation, and everyone is inspired. So I was just a bit following for the previous question. So you talked about the follow-up of what you're doing. So my question maybe is even more general. How do you see the future of hybrid perovskites? So where will we see them soon? In solar cells, near our homes, in displays in every computer, or maybe something else?
Ilya, this is a great question, and my answer to that evolves every year a little bit. For instance, I was very much skeptical of perovskite, and I'm sure. I mean, I'm sure when you asked the hybrid, you meant also cesium. So all of these basically.
As well.
Yeah. but hybrid are way more deployed because of wider tuning of band gap in the red. And so I was skeptical about photovoltaics. Now I'm a bit less skeptical because I've seen some amazing results from China, where they cover huge areas with the sort of demonstrators and all these stable perovskites, large-scale production at no cost, basically. That's kind of puzzled me. And then tandem solar. So one thing is tandem solar cells, where you combine silicon and perovskite so that you get per area way more energy absorbed. I think that has future. Silicon as a and perovskite tandem cell. That easily goes 30+% eventually in the power conversion efficiency. Now, about quantum dots, I think television displays is a reality which is happening. So this, how much market share they will have against conventional quantum dots, it depends. I still believe conventional quantum dots are a bit more thermally robust. And so it might be that, that depending on displays intensity needed to be produced, long-term operation, one or the other. So I don't see conventional dots to be phased out by perovskites, but I hope the perovskites get their share. Now, X-ray and gamma detection is another area where I think there is a good chance that cesium lead bromide may be a good alternative for cadmium telluride for gamma and hard X-ray in some applications at least, which do not require necessarily very long-term operation. Because the only problem with cesium lead bromide, it reached the same energy resolution in gamma rays, but because you need hundreds of volts across the millimeters of material of the external voltage, because of intrinsic halide mobility as a basically solid state electrolysis occurs on a long term, so they decompose eventually. So, but again, I see some companies making huge progress. But of course, there is always the most unfortunate scenario that material which looks promising for many things will not be good enough for any of them, maybe except quantum dots for displays. But on a longer term, far longer term, I believe in these quantum applications. I really think this is a unique opportunity. What you see actually on the screen, the single photon emission, may be more complex photon production with these dots. This could be cool. Could be uniquely, because these are scalable things. Epitaxial dots are also great, but they are just a very narrow subset of 3-5 materials, hard to upscale. If you need arrays, if you need a quantum light source which acts as a multi-array source for illumination or for some sensing, and you need it to be affordable, there is nothing more scalable in terms of quantum emitter and manipulable. So you can print this, you can code, you can do lithography. This is hard to match. Yeah, that would be my answer to the question of Ilya. Thank you.
Quite a nice answer, quite a bright vision.
Yeah.
Thank you.
Thank you for questions. So I see that audience doesn't want to let you go, Maksym, but time flies by, and if there are no urgent questions, I would like, on behalf of all participants, to thank Maksym again, and to say that your success and success of your team inspires us in our fields as well. So thank you for being with us today.
Thank you very much. And may I answer to that? I would say, first of all, it's always an honor to speak at seminars organized by our colleagues from Ukraine, you, whoever else. And I'm also inspired by many of you, all of you basically, by your resilience, many of you by your academic contributions. Ilya, for example, inspired us for one project. Many others. Some of you, I will not go by name, visited our team or collaborated with us. And again, your resilience, your commitment to that the Ukrainian science thrives, I think it's historic. So thank you for that as well.
Thank you, Maksym.
Thank you.
Thank you, Maksym.
Thank you.
Thank you.
Thank you.